Zach?
I don't know what the numbers were, but can you just do one of them to like refresh my memory on what they're? Just do number one.
Okie dokie. So here it asks you to find the value for sine if cosine is this and theta or tangent is that. So I would start with the Pythagorean identity that relates sine and cosine. It says sine squared plus cosine squared, so that's going to be in this case 1/4 squared, is equal to 1. So 1/4 squared is 1/16. I subtract 1/16 from both sides and square root both sides. And I get sine theta is plus or minus square root of 15/4. Okay with that? Okay. Now I just need to figure out whether that sine theta should be positive or negative, right? So to do that, I'm going to use the fact that tangent is sine over cosine. And I know that in the problem, tangent is negative. If I know cosine is positive, sine must be negative. So I'm going to abandon the positive, and we'll just go with negative root 15/4. Is that okay? Amy? 10? Okay. I would start by looking for something algebraic to do. And it's not making a common denominator. Instead, what I would notice is that there's a greatest common factor of tangent present here. That's going to make things massively easier than if you had tried to make a common denominator, which, if you had, it's not a bad idea. But you would see that pretty quickly it gets pretty messy. So far, so good? Now, again, you could make a common denominator here. I'm not going to do that. I'm going to use identities here. I'm going to rewrite cosecant squared. I'm sorry, 1/cosecant squared as sine squared. And 1/secant squared as cosine squared. Because that gets me to sine squared plus cosine squared, which I know is equal to 1. And that's pretty nice, because we're not going to do any better than just a single trig function there, right? Just of x. Yeah. Is that okay? Some sneaky stuff maybe, or not, you know, it's just one of those where it's like, there's lots of things you could have done. Unfortunately, a lot of those things are like rather time consuming, like they make a lot of work and you don't necessarily get you a lot closer to the answer. That's probably the quickest way to get there. Yes, Zach? Sure. Anybody else? Okay. that's fine. We can always come back and ask more about it later. Doesn't mean that you can't ever come back and ask anything more about it, but if you guys are good for today, that's okay. Oh. So today, we're going to talk about solving trig equations. So last time, or in the last chapter, I should say, we asked you to do things like find the exact value of sine inverse of 1/2, right? So to do this, you'd be like, okay, well, the range for sine inverse is -π/2 to +π/2. So we're talking about quadrants 1 and 4. So I'm just going to go to my unit circle and look for where the y-coordinate is 1/2 inside of one of those, which is clearly quadrant 1, that the y is positive. When I pull that, I see that that value is π/6. I'm not going to refer to the unit circle specifically. I'm just going to kind of make a note of what I was looking up off the unit circles. Is everybody okay with that? Again, I know that most of you don't have the unit circle memorized. I would never ask you to have it memorized. You don't need to memorize it. I do, because I've been doing this for long enough that just like it happened. I didn't mean for it to happen, it just did. You know? It's like when you've seen a movie 3 times and you can start reciting all the lines in the movie. You didn't mean for that to happen, it just kind of happened. Same idea here. But that's a problem like we would have done last chapter, right? Doesn't look unfamiliar to something we would have done last chapter. In this chapter, we're going to start dealing with solving these trigonometric equations. And this also looks a bit like a problem that we would have talked about last chapter. But what's different about this problem than what we had done last chapter? Yeah, it's just a variable name. Well, it's not necessarily that it's even degrees. Aren't I missing something that we would normally have? Yeah, in the previous chapter, I would have given you a range of values to find your answer in, right? Well, okay. Well, how many? So that would really narrow it down to just getting one answer, right? Last chapter, these always just had one answer for us. How many answers is this problem going to have? More. More. Infinitely many. If you think about this graphically, what's going on here, the graph of sine, looks kind of like this. The graph of 1/2 looks like this. How many times are they going to intersect? Infinitely many, right? Because it's going to keep going doop, 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 up and down the whole way, crossing over 1/2 over and over and over and over and over again, right? So this has infinitely many solutions. IMS is just my abbreviation for infinitely many solutions. Now, we're not going to stop and just say infinitely many solutions. Oh, we're done. Nah. Because these solutions are related to one another. So if I say I talk about this solution right here, and this solution over here, what do you notice about those two solutions? Zach?
X values,
What?
like they're in different spots on the x-axis.
Okay, they are in different spots on the x-axis. Sure. They're one period apart. Yeah, if I look at this, that makes up like one cycle, right? And similarly, if I compared this x value to that one, that's also one period apart, right? Everybody can kind of see that? Oh, okay. So if I compared this solution and this solution, also one period apart. Everybody see that probably as well? So really, there's two types of solutions. And then there's all the angles that are coterminal to those two types of solutions that are one period apart. Everybody okay with that? So let's show you guys how we'd actually go about solving this then, and how we'd write that answer up. So we'd begin by doing the sine inverse of both sides. Then we'd go to the unit circle and look up all the places where y is 1/2. So that happens at pi over 6, as well as 5 pi over 6. So if I looked at the unit circle where the y coordinate is 1/2, those are the two locations. So those are two of our answers, right? I also want to include any answer that's coterminal to pi over 6. So the way I write that is I'm just going to write pi over 6 plus 2 pi k, where k is an integer. So that's going to include anything that's a multiple of 2 pi away from pi over 6. Jack?
Is that pi over 6 or pi over 5?
Oh, I'm sorry, pi over 6. Thank you. Yeah. Good catch. Again, if I write something down that looks clearly wrong, make sure you interject right away. Mia.
Can we say like plus or minus?
Well, because the integers include negatives, if we're taking k out of any integer, that'll include the negatives. So we got it there. And we can do the same thing then with the 5 pi over 6. We just write the same thing afterwards. So what we're saying is, basically we have two types of answers. We have pi over 6 and everything coterminal to that, and 5 pi over 6 and everything coterminal to that. Because there's infinitely many angles coterminal to each of them, I have infinitely many solutions, but there's really only kind of two types of solutions, right? Does that feel okay? Now, if we had asked for instead to solve this answer from, say, 0 to 2 pi, well, all we need are the two answers from the unit circle, right? No big deal there. But what if our interval was kind of kooky? What if our interval was like negative 5 pi over 2 to positive 11 pi over 2? Yeah. What am I going to do there? Well, I'm just going to kind of use these infinite solutions that we had generated to just keep finding answers until I get things that are outside of my interval. So let's start with the first solution, pi over 6 plus 2 pi k. Pi over 6 is kind of my base solution, right? Uh-oh. If I subtract 2 pi from that, I get 11 pi over 6. That's still in the interval from negative 5 pi over 2 to 11 pi over 2, right? 5 pi over 2 is 2.5. 11 pi over 2 is 5.5. It's between negative 2.5 pi and positive 5.5 pi, right? Because that's a little bit less than, or a little bit more, I guess, since we're talking negatives, than 2 pi, or negative 2 pi. If I subtract another 2 pi from this, I'd be at negative 23 pi over 6. But that answer is too small, right? That's almost negative 4 pi. That's too small. So it won't take that one. So we found all the negative answers. There's just one of them. Now we'll start adding 2 pi's. So if I add 2 pi to 11 pi, or to 1 pi, I end up with 13 pi over 6. That's a little bit more than 2 pi, certainly less than 5.5. That's okay. If I do another, that's 25 pi over 6. It's a little bit more than 4 pi. That's still okay. Less than 5.5. If I add another 2 pi to that, that's a little bit more than 6 pi. That's too big, right? Much bigger than 5.5 pi. So I don't want that solution. So these are the answers that are coming from the pi over 6 plus or minus 2 pi k. Let's get the answers from the 5 pi over 6 plus or minus 2 pi k. So again, 5 pi over 6 is our base solution. If I subtract 2 pi from that, I have negative 7 pi over 6, a little bit less than 1, or a little bit, yeah, less than 1, negative 1 pi. So that one's good. If I do it again, I have negative 19 pi over 6. That's a little bit less than negative 3 pi, which is too small, right? Negative 2.5 is our lower bound, so that's not a solution. So I found all the negative ones. Let's go find the positive ones. So we'll be adding 2 pi to 5 pi over 6. 17 pi over 6, a little less than 3. That's okay, still less than 5.5. Add pi, or 2 pi again. That's 29 pi over 6. That's a little less than 5 pi. Still okay, right? Still less than 5.5. But if I add another 2 pi, that's a little bit less than 7 pi. That's too big. So these 4 are my solutions from the 5 pi over 6 plus 2 pi k. So once we have that infinite solution, it really doesn't matter the interval that we're being asked to solve over. We can just keep generating solutions until we find stuff that's not in the interval. Does that feel okay there? Now, how good you are at adding fractions, that could be varying degrees of easy, but your calculator can handle the fractions, right? We've talked about how to deal with the pi's and the fractions in there before. You just drop the pi's off of it on your calculator, and you can use the frac command on your calculator and deal with it. It's not a big deal. Okay. Let's do some more examples here. So we've talked about the trigonometric part, right? About getting these solutions once we've got our inverse written. Some of the times, though, the algebra to get there is not so easy. So let's look at a couple of examples. Well, probably more than, let's say several examples. Okay. So all these problems that we're going to look at here, we're just going to be solving for 0 to 2 pi. Because if we can solve for this, we can write our infinite solution, which is easy. You just add the 2 pi k on at the end. And if our interval wasn't 0 to 2 pi, once you found our infinite solution, we can just use that to generate all our answers that we need to fit in the interval. So really, this is the kind of core problem for any version of this that we might ask. Is that everybody okay with that idea? Okay. All right, so here we have cosine squared x is equal to 1. What should I do first? Can I just do the cosine inverse to both sides? No, why not? Because it's squared. Great. So what do we got to get rid of before I can do the cosine inverses? We got to square root it. Okay. So when we square root both sides of an equation, what do we have to be careful about? The plus or minus. Good. That's going to make me break this up and think about it as two separate problems. So cosine x equals 1 and cosine x equals -1. Then we can do the cosine inverses. Is everybody okay with what I did there? And then I'm going to go to the unit circle and find the place where the x coordinate is 1. That happens at 0. And really, again, at 2 pi. But I'm not going to write 2 pi. Why not? Yeah, if I look at the interval, notice that the 2 pi has a parenthesis on that end rather than a bracket. Remember that the parenthesis means it's not included in the interval, so 2 pi is not something I would write as an answer. 0 has a bracket, though, so that is included. I would write 0 as an answer. Is everybody okay with that? Good. So if I do the other one, again, we'll go to the unit circle and we'll look for the x coordinate being -1. That happens just at pi. So those are my two solutions. Everybody okay there? Not too big of a deal. If we had asked instead for this to be all possible answers, all we need to do is tack on that 2 pi k to the end of each of these. Does anybody notice anything about these two solutions? Well, the first set of solutions is like 0 pi, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, etc. The second set is like 1 pi, 3 pi, 5 pi, 7 pi, 9 pi, etc. What do you notice about all those solutions? They're really all just 1 pi apart, right? So you could actually combine these two solutions together as a single solution. Instead of saying I get 0 and everything coterminal with that, and pi and everything coterminal to that, I could just say, or I could just have 0 and every multiple of pi of that. Now, if you wrote your answer on a quiz or a test as two separate pieces like we did initially here, I wouldn't mark that wrong. Okay, wouldn't be wrong. But if you look at an answer key of mine, I'm not going to write it as two separate. I'm going to combine them together into one solution because it's a lot less writing to do that. Particularly in the typed out solutions, it's way less symbols to kind of generate on the computer to just do it as a single answer. Is that okay with you guys? You kind of see what I did there? Okay. Let's do, so that's just like a little aside here at the end. I wanted to show you how sometimes you can combine two answers into one in that infinite sense, right? Okay. Let's do another. I think we're on B now. So let's say we're solving 2 cosine squared x plus cosine x minus 1. All these examples we're doing are just from 0 to 2 pi, right? I set that in the beginning part of the instructions, and then we have the letters underneath it. So I know it's not here right now where you can see it, but don't forget that. Oh, boy, this one looks way more confusing, right? What am I going to do with this? Anybody with a good idea? Okay. And then what? Well, 2 isn't a coefficient on everything, right? So then you'd end up with like cosine squared plus cosine over 2 equals 1/2. Okay. But it's not equal to 0, right? If you're going to factor, shouldn't it be equal to 0? Because you can't apply the zero product property without that. But I like the idea of factoring this. And you're right, not every term has a cosine in it. But what if we had written it instead of with cosines? What if we had just written it with a's there as our variable? Cosine x is just a, right? Would you know what to do to solve something like 2x squared plus, or I'm sorry, 2a squared plus a minus 1? You should recognize that equation from last year. What kind of an equation is that?
Quadratic.
Quadratic. How do we solve quadratic equations? Factor or quadratic formula. Yeah, those are the two ways primarily that we would solve a quadratic equation. In this case, which one do you think I'm going to suggest using? I'm going to suggest factoring. Now, it's not wrong to use the quadratic equation here, or the quadratic formula. It would certainly work. I want to review factoring, though, so I'm going to choose to use factoring because it's probably been a minute since any of us have factored anything, right? We haven't done really anything that involved any factoring yet this year. So the first thing you need to remember about factoring is that our rules for factoring are slightly different depending on whether the leading coefficient is 1 or not. In this case, what is the leading coefficient? 2. That's the slightly more complicated case. So what I'm going to want to do is I want to start by finding the two numbers that multiply to give me the leading coefficient times the constant term and add to give me the coefficient on the linear term. So what multiplies to give us -2 and adds to give us +1? Go ahead. 2 and -1. Now, unfortunately, that doesn't take us straight to our answer. What that's going to do is it tells us how to break apart the linear term. So I'm going to rewrite a as 2a plus -1a. Is it starting to ring some bells here? We did this a lot last year. I'm going to make two terms. From the first term, I can take out a greatest coefficient or greatest common factor of 2a. Good. When I take out that 2a, what's left? A plus 1. Right? When we're factoring things out, we're dividing, really. Everybody's okay? If I look at the second group, what's the greatest common factor there? -1. Still doing okay? Notice now that each term has a plus 1 in common. So if I factor off that a plus 1, I'd have 2a minus 1 left. So now we're factored. But remember, in the original problem, really, we weren't solving for a. We were solving for x. So I need to go ahead and put back those cosine x's. Still doing okay? So now I can apply the zero product property and set each of my two factors equal to 0 and solve them separately. So I have cosine x plus 1 equals 0 and 2 cosine x minus 1 equals 0. So the first equation will subtract x from both or subtract 1 from both sides and then do the cosine inverse. I'll go to my unit circle, look up where x is -1, and I find that that's at pi, is the only location there. In the other equation, we'll start by adding 1 to both sides, dividing both sides by 2, then doing the cosine inverse. I go to my unit circle, look up where the x-coordinate is 1/2. That happens at pi over 3 and also at 5 pi over 3. So those are my 3 solutions. So far, so good? Zach?
Does this one now have infinite solutions because it was set equal to 0?
Well, I mean, it doesn't have infinite solutions much in the same way the previous one didn't, because all of these examples were being asked to solve for from 0 to 2 pi.
Oh, okay.
If that had been from -infinity to +infinity, then yes, we would just put a 2 pi k on the end of each of those, and we're good.
Okay.
I only did that piece here because I wanted to show you that sometimes you can combine these infinite solutions into one representation instead of 2 separate pieces.
Okay.
So I just did that as a little hypothetical because I wanted to show you that that can happen because it happens in the answer. You'll see it in the answer keys. And if I didn't talk about it in the notes, everyone would be like, wait, did I do this wrong? And it's like you have to re-explain, you know. Does that make sense?
Yeah.
Cool. Okay. What letter are we on? Is it D? C? Okay. So let's take a tricky one. Let's say we're going to do this. And you might say to me, Mr. Kulik, this does not look tricky. But there's something decidedly different about this than the previous problems that we've seen, right? What's different here? Yeah, we have a coefficient on our x, on our variable. Everybody notice that? And you're like, all right, well, I mean, naively, I'm just going to do the cosine inverse of both sides. I'm sorry, the sine inverse of both sides. I go to my unit circle, look up where the y-coordinate is 1. That happens at pi over 2. So I just multiply both sides by a half, or you can think about it dividing by 2, but yuckarooski, I don't like to think about dividing fractions by anything. And I'd get pi over 4, and I'd be done, right? That's not the right answer, though. Wait, what? Well, why not? What did we do wrong? Aiden?
But when it's a 2x, that means we're like two like full things, so you have to like put it in half.
Yeah, so kind of, but you have the right idea. If we go back to chapter 3, what does this part control? What part of the graph or what feature of the graph does this control? Horizontal stretch or shrink, which affects the period, right? So if the period's getting smaller, maybe those multiple solutions, maybe you're getting more solutions inside of 2 pi than we had normally gotten, right? Or maybe you're getting less if the period is getting bigger, right? Oh, boy. So what is the fix to this? Here's the fix. Is we're going to do this like an infinite solutions problem. So as soon as we use our inverse, we're going to, instead of writing a single solution or the solutions that we pull from the unit circle, we're going to represent each solution as an infinite solution. And then at the next step, when we divide everything by 2, we also have to divide that other part by 2. So really we have pi over 4 plus pi k. So one solution when k is 0, another solution when k is 1, that's still inside of our interval, and a third solution when k is 2, but that is going to be, that's a bad looking 9, too big, right? Because that's bigger than 2 pi. So that's our trick. Whenever we see a coefficient on our variable, got to make sure we're using infinite solutions to generate all of our answers. If you don't do that, you're going to miss some, maybe, depending on how big the interval is. Is that okay? Now that's tricky. That's, again, a geometric reason for why we're doing something algebraically, which is always the hard parts in this course, right? When those two different subjects come colliding together like that. Let's do another one. So let's say we're going to do cosine squared of 3x is equal to 1. Oh, I don't want it to equal 1. Let's equal 1/2. My apologies. Okay, what do you want to do to start this one? Square root both sides. I like that. So that's going to give me cosine of 3x equals plus or minus. What's the square root of 1/2? How about root 2/2? The square root of 1 is 1. The square root of 2 shouldn't be in the denominator. We need to rationalize. That's why we get the root 2/2. So everybody, is that okay? If we need to write that out, we can write that out, but I think we've done enough problems where that we've run into something similar to that probably can get away with just saying it. So then we'll break this into two equations. So far, so good. I'll do my inverse. So I'm going to go to my unit circle and find the places where the x coordinate is positive root 2/2. So that happens at pi over 4, as well as 7 pi over 4. And on the other one, that happens at 3 pi over 4, and also at 5 pi over 4. And each of these needs what? Plus 2 pi k. Everybody with me so far? Do we need to stop and re-explain anything? We're doing okay? Do I just need to slow down for a minute? Yes. Lexi.
How do we know it's not?
Again, all of these example problems we're doing, our interval is from 0 to 2 pi, right? Okay, so still we need to get x by itself, right? So we need to divide both sides by 3 on all of these. I'm really going to think about it really as multiplying by 1/3 personally, but Now, I acknowledge right away that I wrote 3 pi over 12, and that can reduce. I know it can reduce, but I'm going to save all the reducing to the end, since this is not going to be my final answer. I'm going to wait and do all my reducing later, because you're going to find when we do all this adding of fractions we're about to do, just leaving these all in the same denominator the whole time makes your life a little less inconvenient. Everybody's okay there? So far, so good? All right. Let's start generating our solutions now. So our interval goes from 0 to 2 pi, right? So if I convert pi or 2/3 pi to have a common denominator with pi over 12, that'd be 8/12 pi. Everybody agree with that? If I subtract pi over 12, if I take pi over 12 and I subtract 8/12 pi, I get a negative. I can't have a negative answer because my interval starts at 0, so I don't have to worry about those ones. So pi over 12 would be my first answer from this solution. If I add 8/12 pi, that gives me 9 pi over 12. Yes, I know I could reduce that. I'm going to save all the reducing for later. That's still good. That's still less than 2 pi. I add another 8/12 pi. That's 17 pi over 12. That's now still good, right? Still less than 2 pi. Add another 8/12 pi, and that one is too big, right? That's 2 and a 12 pi. Too big. Everybody okay there? Same thing before. I noticed that if I subtract 8 pi over 12, I get a negative. So my first answer is really just 7 pi over 12. If I add 8/12, I get 15 pi over 12. That's still good. Add another, I get 23 pi over 12, still less than 2 pi. But if I add another 8/12, way too big. So those are the 3 answers I get there. Doing the same thing. Again, I don't have to worry about the negatives, so 3 pi over 12 is my first solution. Yes, I know I could reduce that, and I know I could have reduced the 15 pi over 12. I know, we'll get to it. If I add 8 pi over 12, that gives me 11 pi over 12. That's still good. And then 19 pi over 12, still good. But if I do it again, 27 pi over 12, that's too big. Wah, wah. And on to my final one. 5 pi over 12 is my first one. And then 13 pi over 12. And then 21 pi over 12. And then 29 pi over 12. But uh-oh, too big. So these 9 answers are my solutions. Keep in mind that if you're looking at an answer key, oops, not that one, that one. We certainly would have reduced all of those ones that I circled in yellow, right? Those could all reduce. I'm going to leave that part to you guys. It's, I think, fair to assume that's a trivial skill at this point, right? You know, reducing a fraction, yeah, not so bad. But that's why I didn't bother to do any reducing before. You saw that it just made all the addition of fractions a lot easier if I just kept the same denominator the whole way through. What do you guys think? Does that feel okay? That one was rough. There's a lot of solutions to sort through, but it really was the same problem. It just got longer, right? There was no new skill involved. It's just like, okay, so this broke into like 5 pieces and just like I have to do the same thing for all 5 of them, but it's the same thing over and over again and just kind of a tedious pain in the buttocks. Let's do another. You ready to get crazy? I'm feeling crazy. Okay, what do you guys want to try to do first here? Zach?
Divide the tangent to x from the other one.
You'd think that'd be a good thing to do, right? Because it really simplifies the problem enormously. What's the problem with that, though? Because that has a variable in it. Can tan 2x equal 0? Yeah. If it equals 0, what does that mean? We've just divided by 0, which means we're probably going to be losing some solutions if we do that. So although it seems very tempting to want to try to do that first, and it is like the natural first thing that like, yo, that will make this way easier, we don't actually want to do that. Is that okay? Instead, what I would suggest is to get everything onto one side. So I'm going to actually subtract the tan 2x over. Because that's going to make a greatest common factor of tan 2x. Everybody okay there? And now that it's in factored form, we can apply the zero product property and set each of these two factors equal to 0. And we can see now that, yeah, we are definitely dividing by 0 since one of the solutions we're interested in is specifically when tan 2x is equal to 0. You see that now, Zach? Definitely would not have been easy to see that straight away. Ooh. So the tan 2x, we're going to do the tangent inverse of both sides. Oops. So we're going to go to the unit circle and look for, remember, tangent is y over x. So when is y over x equal to 0? Really just when y is equal to 0, right? When the numerator of the fraction is 0, the fraction is going to be 0. Particularly since x can't be 0 if y is 0 on the unit circle, because the origin isn't a point on the unit circle. So going to the unit circle, that gives us 0. And that also gives us pi. And notice here that these answers I can combine together. Right? The first set is 0, 2, 4, 6, 8. The second set is 1, 2, 3, or 1357. So I'm actually going to do that, as it makes the rest of this problem quite a bit easier. Well, I shouldn't say easier. Makes it shorter if I combine these together. I forgot to say k is an integer. That's just sloppy, Mr. Kulik. Okay. And we'll pause here and go and work through the other side to catch up to the same spot. But we'll come back to that piece. Is everybody okay there? I just don't want to forget about the other half of our problem. That's a very Mr. Kulik move to do. You know, you do everything correct and then you just forget about the other half of it that you had floating off the screen there. So we add 1 to both sides. And we'll do the sine inverse to both sides. So go to the unit circle where y is equal to 1. So that happens at pi over 2. And then again, we need the plus 2 pi k's on there. Okay. I'll multiply both sides by 2. So if I subtract 4 pi, I get a negative. Don't want that. So pi is my smallest answer. If I add 4 pi to that, I get 5 pi. That's way too big, right? My interval is 0 to 2 pi. So that's my only answer from over here. I go to the other one. I divide both sides by 2. Again, if I subtract pi over 2, that gives me a negative, so I don't want that. So 0 is my smallest answer. And then I have pi over 2. Pi, but I'm really not going to list that twice because I've already listed it over here. So I don't really need to list it twice. You could write it down twice. It's not wrong to do that, but again, if you're looking at an answer key, it's only going to be listed once. And then we have 3 pi over 2. And then we have 2 pi, but oops! 2 pi is actually too big, right? If we remember, our interval has a parenthesis at the 2 pi, so 2 pi can't actually be an answer for our interval that we're solving in. So those are our 4 solutions. 0, pi over 2, pi, and 3 pi over 2. Is that okay? Also may be worth noting, if we were listing this as infinitely many solutions, if that's what we were asked to give instead of 0 to 2 pi, the solution in green doesn't even need to be included, right? Every solution in green is going to appear as one of the solutions in yellow, right? If we think about it, yellow goes 0, a half, 1, 1 and a half, 2, 2 and a half, 3, 3 and a half, 4, 4 and a half, 5, 5, 5 and a half, 6, 6 and a half, 7, 7 and a half, 8, 8 and a half, 9. So every solution in the green is actually one of the solutions in yellow, so I don't even need the green at all. If I were to list the infinitely many solutions, I wouldn't even list the green one. Not wrong if you do, but if you're looking at my answer key, it would not be there. So again, I want to point these things out that, like, just so you're not confused when you're like, what happened to this solution? It's like, well, it's included in there, so I didn't write it down. How are you guys feeling so far? Is this going okay? Medium? Yeah. Mm-hmm. let's see. Let's do a couple more. Well, maybe just one more. Let's go and do this one. Just because we have because we're going to use a different interval on this one. So let's say we want to solve sine squared x equals sine x, where x is on the interval from negative 4 pi to positive 2 pi. Notice there's brackets at both ends of this. How do you want to start? Divide both sides by sine, right? No, right? We just covered that. Okay, square root both sides. No, that's going to get you a square root sine. That's going to be bad. What should I do? Yeah, subtract sine x from both sides. Get everything all on one side. Yeah, there you go. Okay, now what do you think? Aiden?
Just factor out sine.
Yeah, very good. Take out that greatest common factor of sine. Note that in the problem, sometimes I'll use brackets instead of parentheses, just because it gets a little parenthesis hairy with all the parentheses in there. I'll use a bracket or like the curly brace or something just to kind of make it easier to see where all my parentheses are, gets a little crazy. Just makes it look a little cleaner to me. Cool, so it's factored. What can I do now? Yeah, well, I can set each of them equal to 0. That's the zero product property. Remember, this doesn't work if it's not equal to 0, right? What we did here, setting each factor equal to 0, only works if they're equal to 0. If they're equal to 4, you can't do that. Okay. We'll do the sine inverse to both sides. So again, going to the unit circle where the y-coordinate is 0. That happens at 0 and at pi. Well, let's just say, I guess let's do it this way. This one wouldn't be hard to do if you were wanted to do it just by hand in your head, but we'll do that. And remember, what's our interval that we're solving over in this case? It's not 0 to pi anymore. This problem was different. It was negative 4 pi to positive 2 pi. So it just were 0 plus multiples of pi. Hopefully it's easy to see that it's going to be, that this solution is going to give me all of those guys out of there, right? Remember, the interval we're solving over was different this time. In this problem, it was negative 4 pi to positive 2 pi. So 0 plus or minus pi k, or plus pi k, is going to give me all the multiples of pi that I want out of that, right? Mia?
We only have to do the extra step of dividing if there's a coefficient on the x.
Correct. Yes. Which in this case there wasn't, so I did not have to worry about that. So then I have to deal with the other half here. So again, here we'll go to where the unit circle is, the y is equal to 1. That happens at pi over 2. So what do we get here? We have pi over 2. If I subtract 2 pi from that, I get negative 3 pi over 2. That's okay. If I subtract another 2 pi from that, I get negative 7 pi over 2. That's still okay. If I subtract again, though, that's going to be too small. Okay, well, let's try adding 2 pi's then. So that's going to give me 5 pi over 2. And that's too big, right? Again, our interval went from 4 pi to 0 pi, or negative 4 pi to 2 pi. So my solution is going to be those ones right there. Is that okay? We'll need some practice on it, but it's not so difficult of a skill. Notice that it's really kind of combining the things we did last chapter with the things we did in the first section. We're kind of using some of these identities and using some of these factoring skills, and then going back and using our inverse and reading things from the unit circle. One thing that didn't come up that we didn't mention, in all these problems, when I was finding the inverses, I used the unit circle. Is that always going to have to be the case? It doesn't have to be the case, right? What else could you use if you can't use your unit circle? Your graphing calculator and using the reference triangles like we did in the previous chapter. So keep in mind that that can become a little bit complicated, but we should be relatively good at that by now. We did a lot of practice last chapter. I can't remember in the homework set if that comes up. I suspect not, since it didn't pop up in the homework or in these examples that we just ran through together. Amy? Definitely you should expect a homework quiz before Thanksgiving break. If I were you, I would expect that everyone would have finished the 5.1 stuff that we did by the time we take a homework quiz. So I would say that asking people to have been familiarized with 15 to 46 is maybe too much of an ask, even by Friday this week. But I think having asked people to be able to looked at 1 through 14 by Friday is probably realistic. How does that sound?
Yeah.
Drake?
Can you go back to 5.1? This is the one homework. I want to see what you did for because so what problem did you do?
I did P1. That's the first Pythagorean.
Oh, so yeah, you did the square. Okay.